Good day and welcome to Big Bad Tech. I'm your instructor, Jim Pytel. Today's topic of discussion is sinusoidal waveforms. Our objective today is to examine the properties of both circles and sine waves. We'll learn the significance of radians and degrees and learn to convert between these two positional measurements. We'll examine the circular origins of the sine wave and learn to calculate the sine function at different angles. Additionally, we'll learn how to perform both the sine and inverse sine using a scientific calculator. As we learned in the Introduction to AC Circuit Analysis lecture, available at the Big Bad Tech channel, an AC voltage source is one that varies not only voltage magnitude as a function of time, but also polarity. As a result, current will not only vary in magnitude, but also change direction. Additionally, we learned during the course of this lecture that AC voltage and current waveforms can be characterized as having effective voltage and effective current values, and power can be averaged over time. Prior to closing out the aforementioned lecture, I briefly introduced a continuously variant waveform known as a sine wave. Given commonly available household and industrial AC power can be characterized using a sine wave, it is worth a moment of our time to discuss some of the origins and characteristics of sine waves. Bottom line up front. The intention of this lecture is to skip the rarely used nonsense in a full trigonometry class and focus only on those topics that actually matter to electromechanical technicians. As such, there are not a lot of skills I'm asking you to master. However, I am asking you to master all of them. Although the scope of this lecture is introductory in nature, it's absolutely essential, meaning the content herein is to be considered the minimum tool set absolutely necessary for survival. Yes, there are some Get Smart Quick courses out there that foolishly promise you can perform AC circuit analysis without math. I don't know how, but they are as worthwhile as those ads in the back of comic books that promise you can get your black belt in 2 weeks. Although I'm not requiring you to have math shooting out of your eyes at the end of this lecture, I am asking that you at least demonstrate a certain level of mathematical competency with respect to sine waves. This competency is only attained with a certain amount of effort and practice. Let us begin. First, it should be noted that the origins of both AC voltage and the sine wave itself are rooted in the circle. A circle is characterized by several properties, principal among them being the radius. The radius is the straight line passing from the center to the edge. Diameter, a related property, is a straight line from edge to edge, passing through the center. Radius and diameter are obviously related to one another. Radius is half of diameter, and diameter is twice radius. The radius of a circle can be used to calculate other properties. For example, the area of a circle is pi r squared. Another property of a circle is the circumference or perimeter, being the length of the continuous outside edge of the circle. Circumference can be calculated as 2 pi r. Given radius has a relationship with diameter, one could just as easily solve for area and circumference in terms of diameter. Area would be equal to pi over 4 d squared, and circumference would be equal to pi d. Let's try an example problem. Consider a circular concrete patio with a radius of, let's say, 24 feet. Substituting this value into our area and circumference formulas, we can find that the circular concrete patio with a radius of 24 feet has an area of 1,809.6 square feet and a circumference of approximately 150.8 feet. Note the ratio of the circumference and radius. For this 24-foot radius circle, the 150.8-foot circumference is approximately 6.28 times that of the radius, or more appropriately, 2 pi times that of the radius. If you wanted to do this in metric or some other unit system, you could perform the necessary conversions. However, for the purposes of sine waves, we're going to do something remarkable. We're going to forget about units. Let's say we've got a circle with a radius of 1 unit. This unit could be 1 foot if you're from one of those savage regions of the globe, 1 meter if you're from one of the more civilized regions, or 1 furlong, 1 parsec, 1 rod, 1 cubit, or 1 whatever you want. Regardless of the choice of units, you realize there will always be a constant ratio between the radius and circumference or perimeter of all circles regardless of the choice of units. For example, given a circle with a radius of 1 foot results in a circle with a circumference of approximately 6.28 feet, and a circle with a radius of 1 meter results in a circle with a circumference of approximately 6.28 meters, and so on. If we just said our circle had a radius of 1 unit, whatever that unit happened to be, we could say our circle also has a circumference approximately equal to 6.28 units, or more appropriately, 2 pi units. When expressed in this fashion, the distance around the circumference of a circle can be expressed as a radian, where a radian is equal to 1 radii, which if you recall is 1 unit, whatever that unit might be. Radian is another term for a convenient unit. Given a particular distance along the circumference in units of radians, one can express where that particular point is on the circumference. For example, consider a circle with a radius of 1 unit, a circumference of 2 pi, or approximately 6.28 radians, and the point traveling the circumference in a clockwise direction, starting here. Let's say the point travels a quarter of the circle in the counterclockwise direction. How far has the point traveled? The answer is quite obviously that the point has traveled 1/4 of 2 pi radians, or pi over 2 radians, or approximately 1.57 radians. If the point continued to travel counterclockwise halfway around the circle, it would have traveled half of 2 pi radians, or approximately 3.14 radians. If the point continued to travel in the counterclockwise direction 3/4 of the way around the circle, it would have traveled 3/4 times 2 pi, or 3 pi over 2, or approximately 4.71 radians. And if the point continued to travel counterclockwise all the way around the circle, it would have traveled 2 pi radians, or approximately 6.28 radians. Put your understanding of this concept to the test by determining how far the point has traveled if it initiates travel on the far right-hand side and travels 1/3 of the way around the circle in the counterclockwise direction. And again, if it travels 2/3 of the way around the circle. By all means, pause the lecture and try this on your own. If you perform the calculations correctly, you'll note 1/3 of the way around the circle results in a distance of 2 pi over 3 radians, or approximately 2.09 radians. And 2/3 of the way around the circle results in a distance of 4 pi over 3 radians, or approximately 4.18 radians. Consider yet another scenario in which the point travels 10 times around the circle in the counterclockwise direction. This would result in a distance of 20 pi radians, or approximately 62.8 radians. However, 10 full revolutions around the circle essentially lands us back where we started. The Boy Scouts among you will note that alternative methods of positional measurement exist, notably angles. An observer standing in the center of the circle, watching the point traveling around and around the circle on the circumference, can measure angular displacement with reference to the agreed upon starting point on the far right-hand side. A full circle, for reasons of historical inertia, is defined as having 360 degrees within it. Halfway around is 180 degrees. A quarter of the way around would be 90 degrees. 3/4 of the way around is 270 degrees. Put your understanding of angles to the test by determining the angular position of the point if it initiates travel on the far right-hand side and travels 1/3 of the way around in the counterclockwise direction. And again, if it travels 2/3 of the way around. By all means, pause the lecture and try this on your own. If you perform the calculations correctly, you'll note 1/3 of the way around of the circle results in an angular displacement of 120 degrees. And 2/3 of the way around results in an angular displacement of 240 degrees. As another example, if this point traveled 10 times around the circle, this would result in an angular displacement of not 3,600 degrees, but rather 0 degrees. The point being that angles are ordinarily not cumulative. Any complete revolution lands us back at 0. You know, degrees for our purposes are customarily expressed using decimal representations, and not minutes and seconds as is common for some navigational practices. Also, degrees for our purposes differ with respect to navigational degrees because we're defining positive angular displacement as counterclockwise rotation starting from an origin on the right-hand side. Negative angular displacement would simply mean clockwise rotation. An example illustrating the difference being that negative 30 degrees places us 30 degrees clockwise, as does positive 330 degrees counterclockwise. The point being that negative 30 degrees and positive 330 degrees are therefore equivalent angles. I'll come back to clarify accepted formatting in later lectures. For now, you should simply be aware of this duality. You will note that because positions along the circumference of a unit circle can be represented both with a value in radians and degrees, there should be some equivalency between the two in the form of a unit conversion. The conversion factor is as follows. Given a circle's perimeter is equal to 2 pi radians and equal to 360 degrees, it stands to conjecture that 2 pi over 360 or 360 over 2 pi would both be equal to 1 and can be used for conversion purposes. Allow me to demonstrate. Knowing from our previous calculations that traveling 1/4 of the distance around a full circle places the point at pi over 2 radians. Let's determine the same angular position in units of degrees. Given we want units of degrees and we want to get rid of units of radians, we orient our conversion factor such that units of radians cancel out and units of degrees remain. This results in an angular position of 90 degrees. No duh, that's what we observed earlier, and it makes sense. Let's try this conversion in the opposite direction. Knowing from our previous calculations that traveling 1/3 of the distance counterclockwise around a full circle places the point at 120 degrees, let's determine the length along the circumference in units of radians. Given we want units of radians and want to get rid of units of degrees, we orient our conversion factor such that units of degrees cancel out and units of radians remain. This results in a length of approximately 2.09 radians, or more accurately, 2 pi over 3 radians. Again, no duh. That's what we observed earlier, and it makes sense. By the way, the conversion factors of 2 pi over 360, or 360 over 2 pi, can also be represented as approximately 0.01745 radians per degree, or approximately 57.3 degrees per radian. But I recommend against using these figures for a very important reason. Are you going to remember these conversion factors in a moment of stress? No, you are not. Use the conversion in its purest form and you'll never forget it. A circle is 2 pi radians. A circle is also 360 degrees. They equal each other. Orient the conversion factor such that the units you don't want cancel out and the units you do want remain. Additionally, note radians are customarily most accurately expressed in fractional representations of pi. However, arriving at this fraction is not absolutely necessary for this course. Only an especially cruel math teacher would make you perform this unnecessary step. Again, I'm interested in you demonstrating essential skills in the shortest time possible, not dilly-dallying in fraction land all day. Put your understanding of radian and degree unit conversion to the test by converting between the following measurements. If you're given degrees, find the equivalency in units of radians. If you're given radians, find the equivalency in units of degrees. Also, see if you can get a sense of where these positions physically lie on a circle. By all means, pause the lecture and try this on your own. If you're tracking, you should have gotten the following answers. Pi over 6 radians is equal to 30 degrees. It's right about here on the circle. 45 degrees is equal to pi over 4 radians, or approximately 0.7854 radians. It's right about here on the circle. 3 pi over 4 radians is equal to 135 degrees. It's right about here on the circle. 60 degrees is equal to pi over 3 radians, or approximately 1.0472 radians. It's right about here on a circle. One can divide a circle into 15-degree increments to find the following equivalent positions in this table. If you wanted to, you could do this in smaller 5-degree or even 1-degree increments, but ain't nobody got time for that. You get the picture, and you should be able to perform conversion between radians and degrees and vice versa with little difficulty. Now that we've got a pretty good understanding of those properties that define a circle, let's examine the origin of the sine wave and how the sine wave and circle are related. Simply put, the sine wave is a plot of the height above or below the horizontal x-axis as a moving point travels the perimeter of the circle. I say again, the sine wave is a plot of the height above or below the horizontal x-axis as a moving point travels the perimeter of the circle. At our start point of 0 degrees or 0 radians, the point is 0 units above the x-axis and the value of the sine function is 0. That makes sense. At 90 degrees or pi over 2 radians, the point is 1 unit above the x-axis and the value of the sine function is 1. Again, makes sense. This is the largest distance our traveling point can ever be above the x-axis, given it's confined to the circumference of a circle with a radius of 1 unit. In between 0 and 90 degrees is where the magic happens, and if you think about it, in between 0 and 360 degrees is equally magical, since there exists a degree of symmetry for all 4 quadrants of the circle. Let's travel counterclockwise in 30-degree increments to make our job easy and this diagram somewhat readable. If you want to do this in 15-degree or even 5-degree increments, you're welcome to do so. At 30 degrees, or pi over 6 radians, the point is 0.5 units above the x-axis. The value of the sine function is 0.5. At 60 degrees, or pi over 3 radians, the point is 0.8660 units above the x-axis, and the value of the sine function is 0.8660. At 90 degrees, we again peak out 1 unit above the x-axis, given our unit circle has a radius of 1 unit. Continue travel in the counterclockwise direction. It's a reflection of the first quadrant, only this time we're going downhill. At 120 degrees, or 2 pi over 3 radians, the point is again 0.866 units above the x-axis, and the value of the sine function is 0.8660. At 150 degrees, or 5 pi over 6 radians, the point is 0.5 units above the x-axis, and the value of the sine function is 0.5. At 180 degrees, or pi radians, we're halfway around the circle and back on the x-axis, 0 units above the x-axis, and the value of the sine function is 0. Thus far, this should be making sense. At 210 degrees, the point is 0.5 units below the x-axis, and the value of the sine function is negative 0.5. At 240 degrees, the point is 0.866 units below the x-axis, and the value of the sine function is negative 0.8660. At 270 degrees, we kind of bottom out at 1 unit below the x-axis, given our unit circle has a radius of 1 unit. The sine function at 270 degrees has a value of negative 1. Continued travel in this counterclockwise direction would be a reflection of the third quadrant, only this time we're climbing out of the ditch. Ditches, by the way, seem to be frequented by your lazy lab partner, and they've got a recognizable habit of never climbing out of them. At 300 degrees, the point is 866 units below the x-axis, and the value of the sine function is negative 0.8660. At 330 degrees, the point is 0.5 units below the x-axis, and the value of the sine function is negative 0.5. Finally, at 360 degrees, or 0 degrees, we're all the way around the circle, 0 units above the x-axis, and the value of the sine function is 0. Continued travel in the counterclockwise direction would see this same cycle repeat itself. If we do this same analysis using increasingly smaller angular increments, we get increasingly more accurate representations of the sine wave. Here's a tabular representation of the sine wave in 15-degree increments. By the way, the weird-looking symbol is the Greek letter theta, which is often used as a placeholder for some angle. You note the sine wave has some pretty evident properties. Notably, the sine wave can be divided into 4 quadrants, each representing a quarter turn around the circle. The positive quarters 1 and 2, and negative quarters 3 and 4 are essentially perfect reflections of one another along a horizontal line of symmetry. If you know the positive half, you should know the negative half. Numerical and graphical evidence supports this symmetry. Additionally, note within the positive half, there's a rising first quarter, followed by a falling second quarter that are essentially perfect reflections of one another along a vertical line of symmetry at 90 degrees. If you know the rising first quarter, you should know the falling second quarter. Numerical and graphical evidence again supports this symmetry. Similarly, note within the negative half, there's a falling third quarter followed by a rising fourth quarter along a different line of vertical symmetry at 270 degrees. If you know the falling third quarter, you should know the rising fourth quarter. Numerical and graphical evidence again supports this symmetry. Given all these lines of symmetry, really one can understand a whole sine wave by simply understanding only the first quarter. Again, this should be making sense, and you should be seeing these lines of symmetry both numerically and graphically. If you're not seeing this, by all means pause the lecture and stare at this without blinking until you do so. Other points of interest on the sine wave include a zero crossing going positive at 0 degrees, and a similar zero crossing going negative 180 degrees. In another 180 degrees, full 360 degrees of travel, we're back at the beginning with another zero crossing going positive. Also of interest are 2 peak values, a positive peak at 90 degrees and a negative peak, or should I say valley, at 270 degrees. Given we're using a unit circle, the positive peak is positive 1 unit above the axis, and the negative peak is 1 unit below, or negative 1 unit. It should be noted that 180 degrees separates the positive and negative peaks, as do the zero crossings. You'll note that the sine wave, in addition to all these other properties, forms a shape that, for lack of any other suitable descriptive term, looks like a sine wave. I'm not joking around when I say this, but sine waves have their own unique and identifiable shape. Note sine waves aren't hemispherical in nature, nor are they unduly pointed, or angular, or triangular, or anything other than sine-like. Sine functions, you note, have a steep initial positive slope and rapidly increase in value, only to lay off the gas as they approach their peak value. At the summit, there's a flat spot from which you can get quite a view of the surrounding countryside. There's a slow initial roll-off, which steepens as the sine wave crosses zero and goes negative. The slope then mellows out before bottoming out on yet another flat spot at the bottom of the ditch. Then the positive slope gently increases until it's again pretty steep for yet another zero crossing going positive. Additionally, you note that sine waves spend a significant portion of the positive half above 0.5, being the section between 30 and 150 degrees. Similarly, you'll note that a significant portion of the negative half is below negative 0.5, being the section between 210 and 330 degrees. This means that a sine wave spends more time within a single 360-degree cycle in a region greater than half its respective positive or negative maximums. Given these traits, one might expect the effective value of a sine function to be less than the peak value, but greater than half. More on effective values in later lectures. By all means, pause the lecture and take some time to appreciate these features until you understand and appreciate the sine wave on every level that I do. Trust me, taking a moment of your time to appreciate these unique features of the sine wave is far more productive than spending it memorizing trigonometric identities. Moving on, allow me to tie the previous sections into a discussion about scientific calculators. Long story short, your calculator can do all this calculation for you, but you've got to set it up properly and know how to use it. This section operates under the presumption the viewer is familiar with the Texas Instruments TI-89 Titanium Edition Scientific Graphing Calculator. If you lack familiarity with this calculator, I recommend hitting up the tail end of the DC Math lecture, available at the Big Bad Tech channel. If you've got an alternative equivalent scientific calculator that can perform the same functions, that's great, but you are on your own. If you don't know how to set up your equivalent calculator and perform the exact same functions I'm doing with a TI-89, by all means, get yourself a TI-89 or bust out your user's manual for your particular calculator and figure it out yourself. First, your calculator needs to be in the proper mode. As detailed in the aforementioned lecture, recall I emphatically recommended the calculator be placed in specific operational modes. If you've done so already, you're in the clear, but if you're not, here's a procedure to do so. The single most important key on the TI-89 is the mode key. This accesses three basic setup screens accessible via the F1, F2, and F3 keys below the main screen. If someone tosses you a TI-89 brand new out of the box, you should be able to set it up in less than 10 seconds and be ready to rock and roll. This is equivalent of being able to field strip, repair, and reassemble a firearm in a combat situation. The TI-89 won't work well if it's in the wrong mode, and you need to be able to get it into the right mode as quick as possible. The first F1 screen has four options that need to be set up properly: display digits, angle, exponential format, and complex format. Walk down to the display digits using the down arrow key and then press the right arrow key to access the menu. There should be a list going from 1 to Q. Walk down the list using the down arrow key. The option I'll choose is E, float. Not float 1 or float 12, straight up float. Option E, between D fixed 12 and F float 1. Press enter to save this option. Using the float setting, the calculator spits out answers using as many decimal places as it can, and you're free to round it to the degree of precision required. Most of the time, I tell my students to use the most appropriate engineering prefix and just round it to the tenths place. Don't make a big deal out of this. Use the most appropriate engineering prefix and just round it to the tenths place. I know if you're right or wrong. Walk down to angle using the down arrow key and then press right arrow to access the menu. Walk down the list with a down arrow key. The option I'll choose is 2, degree. Press enter to save this option. This entry is essential for this topic. Walk down to exponential format using the down arrow key and then press the right arrow key to access this menu. Walk down the list with a down arrow key. The option I'll choose is 3, engineering. Press enter to save this option. Walk down to complex format using the down arrow key and then press the right arrow key to access the menu. Walk down the list with a down arrow key. The option I'll choose is 3, polar. Press enter to save this option. Some of these entries in the first page should be familiar to you given our previous discussion, and we'll examine complex format in later lectures. However, directly related to today's lecture, the angle setting establishes degrees as our unit of choice, not radians. Your math teacher may prefer radians, but they're wrong. Angle format must be in degrees for this course. I'll show you how the calculator does conversions between radians and degrees in a moment. Moving on to the second F2 page of the mode function, one can pretty much ignore everything with the exception of the last option, exact versus approximate. Walk down to exact versus approximate using the down arrow key. Press the right arrow to open up the menu options. Use the down arrow key to walk to option 3, approximate. Press enter to select this mode. Most of the entries on the third F3 screen of the mode function aren't super important. In summary, first page accessible using the F1 key. Display digits, E, float. Angle, 2, degree. Exponential format, 3, engineering. Complex format, 3, polar. Second page, accessible using the F2 page, exact versus approximate, 3, approximate. Assuming your calculator has these settings, navigate to the home screen and feel free to follow along. Let's examine unit conversion between radians and degrees using the scientific calculator. First, to convert between radians and degrees and vice versa, one could always perform the unit conversion using the manual procedures mentioned previously. The calculator, however, can do this for you with a minimum of keystrokes. Given your calculator is in degree mode, it assumes every numerical entry is in degrees and not radians unless explicitly stated otherwise. Let's deal with the conversion from degrees to radians first. Let's say we want to convert 30 degrees to radians. Enter 30. The calculator knows you mean 30 degrees, not 30 radians. Then press Catalog. Walk down the catalog entry until you find an arrow key pointing left to right that says Rad. Then press Enter to select it, and press Enter again to perform the conversion operation. The calculator returns that 30 degrees is roughly equivalent to 0.5236 radians, and signifies it's currently violating the previously agreed upon degree standard by enclosing the value in parentheses and putting the superscript R next to it, meaning radians. The conversion from radians to degrees is essentially the opposite. Given your calculator is in degree mode, it'll forcibly reformat everything you feed it into degrees, providing you tell it that what you're feeding it is in units of radians. To tell the calculator you're entering in radians, enclose the value in parentheses and put the superscript R after it, meaning radians. When you press enter, the calculator reformats the entry into degrees. Let's say we want to convert pi over 2 radians to degrees. Enclose pi over 2 in parentheses and then press Catalog. Walk up or down the catalog entry until you find the little superscript R. Press enter to select it, and press enter again to perform the conversion operation. The calculator returns that pi over 2 in radians is 90 degrees as we'd expect. Note 90 degrees doesn't necessitate units for clarification because we've established degrees as the unit of choice. Really, the only way to get this process wrong is to mistakenly enter radians without telling the calculator you're using radians. Unless explicitly specified using parentheses and the superscript R modifier, the calculator assumes everything you throw at it is in units of degrees. Put your understanding of unit conversion using the scientific calculator to the test by converting between the following measurements. If you're given an entry in degrees, find it in units of radians. If you're given radians, find it in units of degrees. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. 3 radians is roughly equivalent to 171.9 degrees. Given 3.14 radians is halfway around at 180 degrees, 171.9 degrees would be just a little shy of 180 degrees. 80 degrees would be roughly equivalent to 1.4 radians. 17 pi over 12 radians would be equal to 255 degrees. And finally, 20 degrees is roughly equivalent to 0.35 radians. Moving on, let's now discuss how to perform the sine and inverse sine function using the scientific calculator. Again, given your calculator is in degree mode, it assumes every numerical entry is in degrees and not radians unless explicitly stated otherwise. To determine the value of the sine function at specific angles, press second sine, the light blue alternate entry above the Y key. Enter the angle of interest, close the parentheses, and press enter. The calculator will return the value of the sine function at that angle. For example, let's use the calculator to determine the value of the sine function at 30 degrees. Press second sine, enter 30, close the parentheses, and press enter. The calculator returns 0.5. Too easy. Put your understanding of the sine function using the scientific calculator to the test by determining the following values to 4 decimal places. It may help to locate these positions on a unit circle and determine how the sine function, the height above or below the horizontal x-axis, relates to this position to check your work. By all means, pause the lecture and try this on your own. Pay attention to example problem 3. Don't walk into this easy trap. If you're tracking, you should have obtained the following values. The sine of 34 degrees is approximately 0.5592. 34 degrees on the circle and the sine function would be right about here. The sine of 247 degrees would be approximately equal to negative 0.9205. This position on the circle and sine function would be right about here. Note our value is negative because we're below the x-axis. The sine of 13 pi over 12 in units of radians would be equivalent to the sine of 195 in units of degrees. This value is negative 0.2588. This position on the circle and sine function would be right about here. Again, note our value is negative because we're below the x-axis. Additionally, note we first needed to convert from radians to degrees because our calculator assumes every number we enter is degrees. Finally, the sine of 900 degrees equals 0. At first you might be surprised by this, but think about it. 1 full revolution is 360 degrees. 2 full revolutions is 360 plus 360, or 720 degrees. Go 1 more half revolution, or an additional 180 degrees, you've got 2.5 revolutions, or 900 degrees, and you're back on the x-axis on the far left side of the circle. It makes sense. Sine of 900 degrees equals sine 180 degrees, which equals 0. Is there a trigonometric identity you can memorize? Yes there is. But why would you do so? Look at it. Circles and sine waves have inherent symmetric and repetitive properties that you can't not see if you're paying attention. Using the sine function in the scientific calculator should be easy. Here's something that will challenge you. Most scientific calculators can also perform the inverse sine operation. The inverse sine, written sine to the negative 1, is essentially the sine function in reverse, meaning at what angle we'll have this sine value. To use the inverse sine function of the TI-89, press diamond inverse sine, the light green diamond entry above the Y key, enter the value of interest, close the parentheses, and press enter. The calculator will return the nearest angle at which the sine function achieves this value. Note, nearest angle doesn't necessarily mean first and only, as we'll learn in a moment. Additionally, note, since the sine wave peaks out at 1 unit, asking the inverse sine function at what angle the sine function achieves values greater than 1 or less than negative 1 is like asking your lazy lab partner to show up to class on time and well prepared, i.e., it's not going to happen. The inverse sine function is valid only between positive 1 and negative 1. To keep this easy, let's first perform the inverse sine for 0.5. We're essentially asking the calculator what angle has a sine value of 0.5. Press green diamond, inverse sine, enter 0.5, close the parentheses, and press enter. The calculator returns 30 degrees, as we'd expect, because yes, as we previously demonstrated, the sine of 30 degrees is 0.5. The problem is, this answer is wrong, and that it only gives us the nearest angle at which the sine function achieves this value. Recall that multiple planes of symmetry exist within the sine wave and the sine function also achieves a value of 0.5 at 150 degrees. Is there a trigonometric identity you can use to remember this relationship? Yes, there is. But why would you waste time memorizing trigonometric identities when you can just look at a sine wave's first and second quarter and realize they're symmetric? The rising positive first quarter's 30 degrees is essentially equivalent to the falling positive second quarter's 150 degrees. Really, there's only 2 points on the whole sine wave where a single inverse sine value is correct. Notably, an inverse sine of 1 is achieved only at 90 degrees, and an inverse sine of -1 is achieved only at 270 degrees. All other values between 1 and -1, 0 included, should have 2 valid answers for inverse sine. Again, there's no shortage of trigonometric identities to memorize, but doing so is far less productive than simply looking at a sine wave and realizing the simple truth. Put your understanding of the inverse sine function using the scientific calculator to the test by determining the following inverse sine values. By all means, pause the lecture and try this on your own. Note, unless you're being asked to solve for the inverse sine of 1 or -1, the calculator is going to give you only one answer, and it's up for you to determine the other. Note the vertical planes of symmetry for the rising and falling portions of the waveform should allow you to find the second value. It may help to locate these positions on the sine function to check your work. Pay attention to example problem 2. You will encounter some weirdness, but you should be able to fight your way out of this paper bag if you've got a reasonable degree of mathematical competency. If you're tracking, you should have obtained the following values. The inverse sine of 0.8 yields 53.1 degrees. Given the vertical plane of symmetry about 90 degrees, one would also expect the sine function to achieve a value of 0.8, also at 126.1 degrees. Corresponding points on the unit circle support these answers. The inverse sine of -0.6 equals -36.9 degrees. What on earth does this mean? Given we've been defining positive angles as counterclockwise travel from our agreed upon point of origin, it makes sense that negative angles are merely clockwise travel from our agreed upon point of origin. -36.9 degrees would be equal to positive 323.1 degrees. Given a vertical plane of symmetry of about 270 degrees, one would also expect the sine function to achieve a value of -0.6, also at approximately 216.9 degrees. Corresponding points on the unit circle support these answers. Inverse sine of 0 yields 0 degrees as we'd expect. This is the 0 crossing going positive point of the sine wave. The corresponding point is the 0 crossing going negative at 180 degrees. Because I threw you a couple curveballs in that first batch of example problems, here's another set just to make sure you're on target. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. The inverse sine of 0.2 yields 11.5 degrees. Given the vertical plane of symmetry about 90 degrees, one would also expect the sine function to achieve 0.2, also at approximately 168.5 degrees. Corresponding points on the unit circle support these answers. The inverse sine of -0.4 equals -23.6 degrees, which corresponds to positive 336.4 degrees. This nearest angle would be right here on the rising side of the negative half. Given a vertical plane of symmetry around 270 degrees, one would also expect the sine function to achieve -0.4, also at approximately 203.6 degrees. Corresponding points on the unit circle support these answers. At this point in time, you may be rightly asking yourself, what the hell does all this sine wave math have to do with electricity? Let's take a moment to answer this very pertinent question. At a very fundamental level, circular rotation is the origin of both the sine wave and sinusoidal voltage. Consider a generator shaft driven by some outside physical force like expanding steam, moving water, or blowing wind. Attached to this shaft is a magnet with a north pole and a south pole. This rotating assembly, consisting of the shaft and magnet, is appropriately enough called the rotor. Outside the rotor is a stationary set of windings called appropriately enough the stator. Every time the rotating magnet passes by the stationary coil, a voltage is induced across the terminals of the coil, proportional to the rate of change of the magnetic field, and the number of turns in the coil according to Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction will be detailed in later lectures. However, for the purposes of this lecture, the generation process can be simplified as the following. When a north pole is close to the stator, let's assume it generates maximum positive voltage. And when a south pole is close to the stator winding, let's assume it generates maximum negative voltage. As the rotating magnetic poles approach or recede from the stator, the circular rotation and resultant induced voltage waveform can be modeled as a sine wave. Given the magnet starts operation at 0 degrees with both the north and south pole equidistant, no voltage is generated. However, as the rotor is driven counterclockwise, the north pole gets closer and closer to the stator, and induced voltage peaks out at 90 degrees. As the rotor continues to drive counterclockwise, the north pole gets further away. The induced voltage during this quarter is still positive, but decreasing. At 180 degrees, the north and south poles are again equidistant, and induced voltage is 0 volts. The other half is essentially a repeat of the first, only a negative voltage will be generated since the south pole is on the business end. As the rotor continues to drive counterclockwise, the south pole gets closer and closer to the stator, and induced voltage bottoms out at 270 degrees. As the rotor continues to drive counterclockwise, the south pole gets further away. The induced voltage during this quarter is still negative, but decreasing in magnitude. At 360 degrees, or 0 degrees, we've done a full circle, and the north and south poles are again equidistant, and the induced voltage is 0 volts. The process then repeats itself. By the way, I have taken great liberties in this simplification that I'll come back to correct in later lectures. For now, just put your hand on top of the internet and repeat after me. I, state your name, believe. The point being that the very act of generating voltage has its origins in circular motion, and no wonder the resultant voltage output is sinusoidal in nature. Additionally, we'll learn in later lectures that given sinusoidal voltage input, output current is also sinusoidal in nature for passive electronic components like resistors, inductors, and capacitors. In summary, everything is sine waves from this point on, and you've got to know how sine waves work if you wish to succeed in AC circuit analysis. This being said, if everything's a sine wave from this point on, we might be able to derive some usable shorthand that saves us time and effort. All this and more awaits. Until then, this concludes this introductory lecture on circles and sine waves. In conclusion, this lecture examined properties of both circles and sine waves. We learned the significance of radians and degrees and learned to convert between these two positional measurements. We examined circular origins in the sine wave and learned to calculate the sine function at different angles. Additionally, we learned how to perform both the sine and inverse sine function using a scientific calculator. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.